Okay, dear student, let us see what is there in this question. Photons of a wavelength 468 nanometer are incident on a metallic surface. The maximum kinetic energy of the emitted electron is 1.8 electron volt. Calculate the work function of the surface in EV. So we have to find the work function. This question is from the photoelectric effect, which is which topic? I believe topic 12, I think. I'm not sure about it, but anyways, okay, no problem. So this is the metallic surface, and this is photosensitive metallic surface. So when when the energy is coming onto this surface, like they are closed in a conduit, you can say, or something like that. So this is another cathode, and so they need not to be having any battery, by the way. So they can be connected without anything. Like there is only emitter here, and they are connecting this thing like this. So when the light is exposed, like this surface is exposed to the light, and light is illuminating the surface, what happens is that it is getting electrons out. So electrons jump out of it and they start moving. Like they have certain kinetic energy, so they keep on moving towards the other plate, and that is why the current is there and the current is not zero even without the battery. Now the wavelength of the photons, the incoming photon, is given as this. So we know that the Einstein equation is given by hc by lambda, which is the energy of the incoming photon, which is actually absorbed by the electron now. So this is converted into two things. Number one is the work function. Work function is defined as, like, you can call it w0, or in many books it is written as phi 0, like whatever thing, like symbol that you can use. Work function is defined as the minimum amount of energy that has to be given to the electron so that electron jumps out of the metallic surface. So this is defined as minimum energy. So this is the minimum energy, plus the rest of the energy will be obviously the maximum kinetic energy. So work function, like there will be some electrons, those who would be only at the surface of the metal surface, so the work function will be very less, and that electron will be having the maximum of the kinetic energy. There is a chance that there will be electron which are like embedded in between, like with well deep within the surface, and so work function becomes very high. Obviously the leftover energy is very less, and that is why the kinetic energy gained will be smaller in those cases. So some electrons will be having more kinetic energy, some electron will be having lesser kinetic energy. There was this question also, I think, in paper one sometime, and the question was, do all the photoelectrons which are coming out of the metal surface, they have the same kinetic energy? So clearly the answer is no, they do not. Some electrons are moving at a faster speed and some electrons are moving slowly. Okay, so this is the equation that we are going to use. Now the wavelength is given as 460 nanometer. We can just plug in our values here. Negative 34, C is this, and the wavelength is 468 nanometer. This is hc by lambda, that is energy of the photon. Negative the maximum kinetic energy. So maximum kinetic energy is in EV, and you want the answer in EV. So it will be better if we convert hc by lambda, which presently is in the unit joule. We have to convert it into electron volt. How? By dividing it by the charge on an electron. So this is the conversion factor, I will say, and this is how you convert joule into electron volt. You divide the energy by the charge of the electron, and so whatever is the new numeric value, that will be energy in electron volt. So this is energy in electron volt. When we solve this, we subtract from like 1.8 from this, so you would be getting the work function. So I am not doing anything here, we will not be calculating it. So we will directly move to the mark scheme and we will see if they have done the same thing. Okay, yes, so this is the mark scheme in front of you. Emax is given as hc by lambda minus work function. As I've already told you, I wrote it as W. They are writing it as phi. So this, and so phi is equal to hc by lambda minus Emax. One is the same thing. So this is hc lambda, and this is to convert joule into electron volt. And we would be subtracting 1.8 out of it. So you are getting 0.86 electron volt. always remember that we when we would be making calculation, we can calculate it in any decimal, but at the end of the day, when you have to report the answer, your final answer should be having two significant figures. So the two significant figure is 0.86. So this electron volt will be the work function for that metal surface. Okay, let us now move next. Remember that this value is 0.86 ev. 0.86 ev. Yeah, now let us go for the next. The longest wavelength of the photon that will eject an electron from the surface. So coming back to the Einstein equation, hc by lambda is equal to work function, and the rest of this will be given out as the kinetic energy. But as I've told you that this, when you use Ke max, you are basically talking about a particular electron for which the work function was minimum. But there is a possibility that the work function is different, like some kinetic energy is not this, and there are a couple of other things also. But in this case, what we do, we are going to mess up with the wavelength of the photon. So there is a minimum wavelength which is known as threshold frequency or threshold wavelength. Lower to that, like from frequency point of view, lower to the frequency, from wavelength point of view, you cannot have more wavelength. So this is the maximum value of the wavelength that you can choose if you want to get an electron out. So the longest wavelength will be, like you see, the energy of a photon is hc by lambda. Now longest wavelength means lesser energy, so minimum energy to get an electron out of the metal surface. So that can happen if we are taking this kinetic energy to be zero. Let us say that all of the energy of the photon, like it is not that enough, but only that the electron is able to get out of the metal surface, and it will be having zero kinetic energy once it's get out of it. So this will be related with zero. So work function is equal to hc by lambda, and we want to find the wavelength. So this wavelength will be the maximum possible wavelength, or c by lambda is the minimum frequency. So both you can find threshold frequency or threshold wavelength. So this will be the equation. Again, I am not uh, calculating it, like work function is 0.86. Accordingly, plug in the value, get the answer. So sorry, yes, hc by lambda is equal to work function. So kinetic energy in this equation is taken to be zero, as I've already told you, and you divide it by the charge of electron, and so you create this into ev, because this is ev, so you have to convert it into joule, because here for the wavelength you want the answer in SI unit. So EV has to be converted into joule. Okay, so even this is done, even this is done. I don't think that there will be any problem here. Let us go to the next question now, 8b1. In an experiment, the alpha particles of initial kinetic energy 5.9 mega electron volt are directed at a stationary nuclei of lead which is having mass number 207 and the proton number as 82. Show that the distance of the closest approach is about this. So we want to find the closest approach. Now this is a different topic, like again it is topic 12, the Rutherford experiment that we did, and in that we learn about the closest distance of closest approach. So the earlier question, that is 8a, was about photoelectric emissions, and this is about the Rutherford Geiger Madsen experiment, in which like they were using the gold film and they were bombarding the gold film with alpha particles. This is what is happening here. Now, what is the distance of closest approach? So how do we define it? Let us first understand. Let us say this is the nucleus, and there is a alpha particle here, so it's really far away. That is why I have drawn it in a very weird manner, like alpha is on the other end. So this alpha is having some kinetic energy. So what is the potential energy of the alpha? The potential energy of this alpha will be taken to be zero. Why? Because it is really at far away distance, like kind of infinite. So if it is at infinity distance and we say that there is no interaction present between the alpha particle and the nucleus as of now. So the potential energy will be taken as zero. Now they're coming together. So the charge on alpha is plus 2e. Why? So many students would be having a problem like, what is alpha? Alpha is the helium nucleus. So we can say the atomic mass number was 4 and the atomic number is 2. It means like there are 2 protons and 2 neutrons. Obviously the helium will be having 2 electrons also, but we have to remove 2 electrons. So you remove 2 electrons, so you are left only and only with the nucleus of helium, and the nucleus of helium is containing 2 protons and 2 neutrons. So these 2 protons and 2 neutrons are there, and this alpha is coming. This is called alpha, or you can call it helium nucleus. So this is having a charge of 2 plus, it is coming towards this. It is having only and only kinetic energy and potential energy 0. Let us say it is directed directly towards the nucleus. It is going to hit head on, like from on the central line. Obviously this is also positively charged, and Z is the proton number. So I can say that Ze is the charge of the nucleus. Like you're talking about gold, you're talking about lead. So in the case of lead, it is 82. It means that the nucleus is the house for 82 protons. One proton is having charge of E. So the charge here will be 82E. Instead of Ze, we can write it as 82E because this is the nucleus of lead. Now it is coming together, and after some time, like this is the closest of all the distances that it is able to go, the nearest distance towards the nucleus. And at this point it loses all of its energy, it stops here, so the final velocity becomes zero, which clearly means that at this point the kinetic energy becomes zero. Now, if kinetic energy is zero, so where is that energy gone? That energy has converted itself into the potential energy. So kinetic energy is equal to potential energy, and this distance is small r. So when the alpha reach at this point, it will be plus 2e. So all of the energy will be in potential energy. Earlier, all of the energy was kinetic energy. So clearly, we can create a mathematical equation here. Kinetic energy is equal to the potential energy of the system afterwards, which will be equal to, from the concept of electrostatic, topic 5, or you can call it topic 10 because we're talking about potential energy. This capital Q into small q divided by r, where r is the distance of closest approach, obviously, because that is the minimum distance. This is the potential energy. This will be equated with ek, that is kinetic energy. Now kinetic energy is given as 5.9 10 raised to power 6 EV. So EV has to be converted into joule. Okay, so because on the left hand side you have the energy and the unit is electron volt. On the right hand side you have the potential energy and the unit is joule. So either you divide joule by the charge on electron, or you multiply the kinetic energy with the charge of electron. Anyways, one is the same thing because we want to have same unit on both sides. So this, and K value is 9 into 10 raised to power 9. Capital Q value is 82E, and small q is 2e divided by r. So this 1e and 1e can be cancelled. So accordingly, we can find the value of r from this expression. Again, we are not going to do anything as of now. You can use the calculator and you can see that yes, you are getting the answer indeed, which is similar to 4 into 10 raised to power negative 14. But let us go to the mark scheme and see what is written there. Now here the charge is 2e, then the other charge is 82e. So the distance of closest approach is k capital Q small q divided by the kinetic energy, which is given as 5.9 mega electron volt. So they have done exactly the same thing that I had written, and you can now just take up your calculators and you can calculate that value that I have given you. So the value is coming out to be equal to 4 into 10 power negative 14 meters. So this is how we do this question. So 8b1 is also done. Let us now move to 8b2 and see what is the next question. I tried to explain you the complete concept of the distance of closest approach, so I think that should be justice that we have done here. But let's say any comments that you have, please do mention that in the comment section, no problem. The radius of nucleus is this. Now, the radius of the nucleus is found to be 7.1 10 raised to power negative 15 meters. Suggest why there will be no deviations from the Rutherford scattering experiment in B1. There will be no deviations like the experiment that we have done now. So that will be showing you the results similar to the results that we predict with the help of Rutherford scattering experiment. So there will be no deviation in our experiment and the experiment done by Rutherford at that time. So why do you think that we would be finding the similar results? Why will we find that kind of thing is, you see that in the other question we found the distance of closest approach, and the distance of closest approach is found to be 4.0 into 10 raised to power negative 14 meter. This is the distance of the closest approach. Now Rutherford said that yes, it will be happening like this only. There will be a distance of closest approach which will definitely be more than the radius of the nucleus, because these two nucleuses are actually not going to hit each other. They are not going to come near to each other within the range of a nuclear distance, we cannot say. So there will be a big gap, and definitely there is kind of 10, the factor of 10 is there, which separates it. It means like the distance of closest approach is 10 times bigger than the radius of the nucleus. So this is r, and so 10 times away is the alpha particle that is coming, and it was stopped at this distance. So it is 10 times the radius of the nucleus. So it's very, very far away. So it is not able to bridge the distance with this much of the kinetic energy. The distance is still big. It is not in the nuclear range of Fermi meters, and that is why there will be no deviation from the Rutherford experiment. Because if the distance becomes very small, then nuclear forces also starts acting. As of now, the alpha particle is far enough, and so the nuclear forces will not be having any influence on the alpha particle. What is that distance up to which the nuclear forces show an influence? That is nearly 2 to 3 Fermi meter, that is 10 raised by negative 15 meters. This is the distance that the alpha particle needs to come into, but it is very, very far away, like it is multiplied by 10. So kind of it's like 10 times this distance. That is why there will be no deviation. But anyways, let's see how they have explained this thing. So the closest approach is significantly larger than the radius of the nucleus, and it is far away from the nucleus. Therefore, strong nuclear force will not act on the alpha particle, absolutely as what I have said. You can refer to the book like Soko's, and there is a graph given there, and they show you that this was what was expected in the Rutherford's theory because of the mathematical expressions that we have. But after it reaches some distance within the nuclear range, immediately there is a deviation from what is expected from Rutherford's theory, thereby proving that nuclear force exists, isn't it? So this is it, my dear students. So this is how this question is done. So this was the last question for this paper 2 May 2023 times on 1 HL. I hope all of the questions will be very clear to you now, and if there is any other problem, you people can message me on WhatsApp, or you people can message me in the comment section, no problem about that. Okay, dear students, after this we would be moving to some other question. All the best. Bye.